Good morning. Today is Monday, April 6th, and our goal today is to define, graph, write, and determine the domain of square root functions. This is the first lesson in Unit 10, and it's the first new learning we've had since we've been trying this online learning thing. So a strong recommendation to all of you who have been kind of picking and choosing which assignments you're doing. Now is the time that we really should buckle down and make sure that we're doing each assignment each day and giving me feedback as necessary about whether it's the right amount or if at any point it becomes too excessive to do on one day. So you just finished some problems in your journal that were designed to get you ready for this lesson. I'm hoping that you used a table to graph those square root functions, and that you felt like you were reasonably successful in graphing them. But if you're not, no worries, we'll catch you up here in just a minute. So first let's start with defining a square root function. It's basically a function that has a square root symbol, and the independent variable is in the radicand. So the parent function is y equals the square root of x. That's the first one that you graphed this morning. And again, I hope that you used a table to graph it. So my suggestions for you as you're graphing these square root functions are to start by making a table. I'm going to show you how to find the vertex, and I put vertex in quotation marks because it's not really a vertex, but it acts like a vertex. So we'll look at that in just a minute and see why it's not really a vertex. And then we want to look for the pattern. So again, I'm hoping in this for this graph that you just made a basic table, and if you're have 0, 0, 1, 1, 4, 2, I don't want to use a value for x that's going to end up with some weird value for y. So if I were making this table and I wanted one more point just to see the shape of my graph, the next one I would use is 9, because the square root of 9 is 3. So if I were then, that's where that point was. So my graph is going to look something like that. And again, that's the parent function of a square root function. I want you to notice that, say for example, I used 4. So y equals the square root of 4. We know from the work we've been doing with quadratic equations that there's really 2 roots to the square root of 4. So it would be positive and negative 2. So on each of these, I would have also the negative root. That will be down here. But notice that if I'm going to sketch that piece of the graph in. If I include this part of the function, if I include that negative root, it's no longer a function because it no longer passes the vertical line test. So when we're working with square root functions, we only use the positive root, and we don't use these negative roots. Again, because if we did, it would no longer be a function. So that's basically our parent function. When I say to find the vertex, it's really not a vertex, because when we were working with quadratic equations, the vertex was the minimum or the maximum. And so this is not necessarily the, it doesn't really, I guess it's a minimum, but it doesn't really fit that definition. So even though 0, 0 in this case is kind of our starting point, we don't call it the vertex. That's why I put it in quotation marks. But notice, take your computer and turn it 90 degrees counterclockwise. And if you do that, it looks like you have part of a parabola. And in fact, square root functions behave a lot like parabolas laying on their side. So if this were to be my quote vertex, I'd go over 1, up 1. I'd go over 2, up 4. I'd go over 3, up 9. So it's following the same pattern that that our quadratic equations did, or parabolas did. So these were the other three graphs that you did in the warm-up in the journal. So again, I made a table for each of them. I looked and found what I would say is my starting point, where I'm going to start that graph. So I've got 0, 2, 1, 3, 4, 4. Again, notice if I call this the vertex, I'm going up 1, over 1, up 2, over 4, up 3, over 9. So that would be another point. So my graph looks like a parabola laying on its side. Notice by looking at just the equation, this part is the parent function, that plus 2 behaves a lot like the k did when we were working with y equals x minus h squared plus k. The k is outside of the parentheses that are being squared, and it shifted my equation up and down. The same thing here, this plus 2 is shifting everything, it's shifting my parent equation up 2. This equation, on part C, this equation, notice that the 1 is underneath the radical symbol. So this is more like the h when we were looking at vertex form of a parabola. So this tells me that my beginning point is going to be at -1, 0, because I have a plus 0 out here. So in fact, that point is one of the points in my graph, that -1, 0. So that's actually where my graph is going to start. I also have 0, 1, and I have 3, 2. I did not graph that correctly. Erase. I've got -1, 0, 0, 1. I could tell when I started to do that, I could tell by the shape of my graph that it wasn't right. So I'm going to do one more out here. If I had, I want this to be 8. 8 plus 1 is 9. The square root of that is 3. Plus 0 is 3. So I've got 8, 3. I also could have found that by, again, starting at my vertex, going up 1 over 1, up 2 over 4, up 3 over 9. So then I am going to recognize that shape each time. So there's my lazy parabola on its side, but only the positive root of it. On my next one, the same kind of situation. I'm going to plot some points. On this one, I've got 0, 0, 1, -1, 4, -2, and I am noticing that my function is the mirror opposite of the parent function, and that's what that minus is doing. So just like with a parabola where the negative a turns the whole thing upside down, this creates that mirror reflection on the lower part of my graph. So again, if I were thinking of calling this beginning point a vertex, my vertex in this case would be 0, 0. Let's look at that with a little bit more complicated problems. So these next two problems, I really want to draw your attention to the similarity between this square root function and the vertex form of a quadratic function. So if I were thinking about this as a quadratic function, this would be h and this would be k. So I can use that same idea here. So my h is going to be 1 and my k is going to be 2. That's going to be my beginning point in this function. My a, there's nothing there, so it is 1, tells me that it's going to follow the normal pattern. So from that point, I'm going to go up 1 over 1, up 2 over 1, 2, 3, 4, up 3, 1, 2, 3 over 9. So my function is going to look like this. And let's just check that, especially when I'm learning how to do them. I'm going to make sure that I check it with a table. So I know that 1 and 2 was one of my points. So I'm substituting 1 in for the x. 1 minus 1 is 0, plus 2 is 2. If I substitute 2 in for x, 2 minus 1 is 1. Square root of 1 is 1, plus 2 is 3. And the next number I want to substitute in is going to be a 5, because I want to choose values that I'm able to find the square root of it. So if x equals 5, then 5 minus 1 is 4. Square root of 4 is 2, plus 2 is 4. So again, I'm just checking some of the points I already have on my graph, so I feel pretty good about that one. Notice that whatever is under the square root symbol has to be positive, because we know that if it's not 0, sorry, it also could be 0. Because if it ended up being negative, the square root of a negative number is an imaginary number, which we're not dealing with yet. So this has to be 0 or greater. So my beginning point is always going to be where this equals 0. So 1 minus 1 is 0. That's why I'm going to start at x equals 1. I would never, I can't substitute a 0 in there. I can't substitute a negative 1 in there. So notice that in this case, my domain is going to be all numbers where x is greater than or equal to 1. So we'll build on that idea as we go forward in these. I'm going to go on to the next problem, and again I'm going to use this idea of the fact that this looks pretty similar to vertex form with an h and a k. So in this case, my quote vertex, again, it's not really called a vertex, but if I were in charge of the world, I would call it vertex. My vertex is going to be at negative 1, 1. So again, it's negative 1 because the equation would be x minus negative 1. And then this is just plus 1. So minus 1, 1. That's my beginning value. Then I'm either going to make a table or I'm going to follow the pattern. Notice in this case that a is 2. So that basically is going to double all of my y values. So if I want to follow the normal pattern of going up 1 and over 1, I actually have to go up 1 and over 2. And then I have to go up 2 and over 8. So it's doubling each of those y's. So it's going to look like this. Again, especially when I'm first doing these, I want to make sure that I've got the shape of it correct. So I know that negative 1, 1 is going to be my vertex. All right, sorry, this is a rough little transition. I just stopped videoing it and I couldn't remember exactly where I was. I was doing this problem, but I had started it, so I'm sorry, it's blank right now. I'm going to think about this as my vertex being negative 1, 1. And so that's going to be this point. That's going to be where I start. And I'm going to recognize that a equals 2. And because a equals 2, I know that I'm not following my normal pattern of up 1 over 1, up 2 over 4. So I want to make a little table and at least start my table to make sure I've got the pattern correct. So I know that negative 1, 1 is in my table. The next point, I want to have this be something that I can take the square root of. So I could take the square root of 0. So, excuse me, I could take the square root of 1. So if I put x equals 1, then this square root is going to be 1 times 2 is 2, plus 1 is 3. The next point I'm going to use is x equals 3, because 3 plus 1 is 2. 3 plus 1 is 4. Square root of 4 is 2. Times 2 is 4, plus 1 is 5. So those are my next 2 points. So you'll notice the shape of this function is a little bit different because that A is making everything a little exaggerated.